Here are the 9 GRASP principles. 1. Information expert. Assign the responsibility to the class that has the information needed to complete the task. 2. Creator. Assign the responsibility for creating an object to the class that will contain or aggregate it. 3. Low coupling. Minimize dependencies between classes to reduce the impact of changes and promote reuse. 4. High cohesion. Keep classes focused on a single responsibility to improve maintainability and understanding. 5. Controller. Assign responsibility to the object that receives and coordinates events or user input. 6. Indirection. Introduce an intermediate class to decouple two classes that have a direct relationship. 7. Polymorphism. Use polymorphism to support variations in behavior or type. 8. Pure fabrication. Create a class that does not represent a real-world entity but provides a specific functionality. 9. Protected variations. Create a stable interface for a part of the system that may have different implementations. Absolutely. Here's a technical narrative of the GRASP principles without code, focusing on real-world software architecture concepts and the reasoning behind responsibility assignments. 1. Information expert. When you're assigning a responsibility, such as calculating a total, validating a form, or formatting a report, the information expert principle tells you to assign it to the class that has the required data. For example, in an e-commerce system, the shopping cart knows which items are added, and each item knows its price and quantity. So, it makes logical sense to assign the total calculation responsibility to the shopping cart, rather than delegating it to a controller or utility class. Result: this leads to low coupling and high cohesion because each class is responsible for behavior closely tied to its own data. 2. Creator. The creator principle guides which class should be responsible for instantiating another class. If a class contains, aggregates, or closely uses instances of another class, it should be the one to create them. For instance, if a cart manages multiple cart items, the cart should be responsible for creating those items. This ensures object relationships are naturally formed, and encapsulation is preserved. Benefit: this avoids excessive dependency on external factory objects and keeps the construction logic in the context where it is most meaningful. 3. Controller. The controller principle suggests that an interface or use case coordinating class should handle system-level events, for example, user actions like checkout or place order. This class acts as the intermediary between UI and business logic. For example, when a user presses the checkout button, a controller handles the event, delegates tasks to the relevant domain objects, like creating an order, processing payment, etc., and returns a response. Why it matters: this separates concerns and prevents business logic from leaking into UI classes. 4. Low coupling. Low coupling is about minimizing dependencies between classes. When two classes are tightly coupled, a change in one will likely break or require changes in the other. This leads to fragile code. Applying this principle means using interfaces, dependency injection, and stable abstractions. For example, a business logic class should not depend on a specific database implementation but on a generic repository interface. Effect: the system becomes more modular, easier to test, and flexible to change. 5. High cohesion. High cohesion refers to how focused a class is on a single responsibility. A class with high cohesion does one thing and does it well, whereas a low cohesion class does many unrelated things. In a well-designed system, for instance, a class that processes payments should not also send emails or update inventory. Those concerns belong to different components. Result: smaller, more understandable, reusable, and testable classes. 6. Polymorphism. Polymorphism allows different classes to be treated through a common interface. The GRASP polymorphism principle states that when behavior varies by type, define the varying behavior in a polymorphic way, letting the specific classes handle their own implementation. For instance, if you support multiple payment methods, like PayPal, Stripe, bank transfer, each should implement a shared interface, rather than being handled through if/else conditions. Value: you gain extensibility. New behaviors can be added without modifying existing logic. 7. Pure fabrication. Sometimes, to maintain separation of concerns and promote reuse, we invent classes that don't represent any real-world entity. These are pure fabrications, non-domain classes that serve infrastructure concerns. Examples include logging utilities, persistence managers, or data mappers. They're not part of the business model, but they help enforce clean architecture principles. Why it's used: it increases cohesion and reduces coupling, even though the class doesn't map to the domain. 8. Indirection. Indirection is about inserting a mediator or intermediary to decouple two parts of the system. Rather than a UI directly communicating with a database, it goes through a service or repository. This layer of indirection absorbs changes and isolates unstable parts of the system, promoting flexibility and clarity. Outcome: better decoupling and improved adaptability. Though it adds complexity, it's justified when variation is expected. 9. Protected variations. This principle is a strategic approach to designing for change. You protect parts of the system from variations in other parts by introducing interfaces, abstract classes, or other stable boundaries. For instance, if you use an external payment service, you wrap it in a local interface, payment gateway, and let the rest of your system talk to the interface, not the external provider directly. Payoff: when the provider changes, or you add another, the rest of your system remains unaffected.